Niccolo Izzo, and together with Silvano Seva, we'll be presenting this ReverseIt course of this year. This course is presented by Politecnico Open Unix Labs, which is the Linux user group of Politecnico di Milano, which is probably some of you already know it, some of you don't. For those who don't, POuL is a very active association in organizing every year several courses about open source technologies like Linux, first of all, but also Python, machine learning, other stuff, everything using open source tools as much as possible. The ReverseIt is one kind of a typical course in the offerings of the POuL, in which it is basically targeted at people who want to reverse engineer. And this might seem a little out of scope with respect to, open source software development. However, it's not, because all the devices that we use, many of those, let's say most of those, are inherently proprietary, either because the vendor doesn't have the time, or maybe it doesn't seem convenient to publish detail about his internals. So we have two roads. Either we start to design our own devices, and this is something which we obviously we have to do. But sometimes it's also it could be a road to take an existing commercial device and start to reverse engineer it and try to run our own code on it. This is very interesting because commercial devices are cheaper than a device we could make. They are scalable. They could be found on the market. Therefore, if you take a commercial device, if you develop some firmware for it, and basically let out that firmware in the wild, lots of people would be able to buy the device freely on the market, because you won't have to the problem of scaling the production, and they can be able to run open source code on it. So this is the purpose. At least this is the vision of this year edition of the ReverseIt course: how to take proprietary hardware, which is cheap, which is easy to find, how to reverse engineer it, its firmware, its hardware, to create some custom. Sorry, I will mute. Okay, I will mute everybody of you. So we will take proprietary devices and reverse engineer it, which will be a very difficult but very fun activity, with the purpose of running our own code and be able to finally control and really possess the devices which we bought. So let's start. I mean, we will see in the detail how to jailbreak a device, which means how to bypass the embedded security protections of a device. The device of which I'm talking is this radio, which is the Titera MD380. Okay, it's a Chinese radio which is out there since 2013. It's broadly available. It costs less than 1,000 euros, so it's kind of affordable. And this radio became famous because it was one of the first radio which was reverse engineered by the community, and people starting from the work of Travis Goodspeed, which is a recommended account to follow on Twitter, obviously. People started analyzing the code which runs on the radio, they were able to create a patched version of its firmware, which enabled to implement some functionalities which were not present on the radios. But the story of this radio does not end here, but we will see that in the last part of this episode of the ReverseIt course. So what we want to do in particular, the first thing we want to achieve, the first objective when we have a proprietary device on our hands is to dump the firmware. This is because when we have the binary of the firmware in plain text form, so if the radio or the device employs, basically everything that I'm saying is applicable also to other kinds of embedded devices, not only to radios, but this is the example we will bring you here. So once we have the firmware image of the device, we are able to decompile it. And by decompile it, we can infer many things, like we can understand how the underlying hardware works and start, for example, building our own application, maybe from a little demo which takes the LED on the platform and simply blinks it, okay? Doing something like this, if you know anything about the platform, can be really challenging, but also really rewarding after you do it. And one way to do this is really to start obtaining the original firmware. But also, if you want to understand more about how some functionalities of the original firmware are implemented, you can also decompile the code, for example, to understand the binary formats which might be used by such code. For example, this radio has in it some calibration settings which allow to properly tune the transmission parameters, so that because each radio is a bit different from the other one when it comes out of the factory. And by calibrating this radio, you ensure that you are, for example, transmitting with the correct amount of power, or not that you are not burning your device, because this device pulls out of this tiny antenna 5 watts of power, which is something that, if wrongly put, can really fry any circuit. So we have the calibration data of this device. We can dump it because normally you cannot, but we might be able to dump it because it is stored in an external SPI flash, which we can access with some clips, hardware clips. And however, once you dump it, it's just a bunch of binary data. And really trying to understand the purpose of each field simply by, for example, changing the values and trying to transmit and see how the transmission changed, it might be an awful procedure, because it would be, this radio has like tens and tens of different parameters, and really the best way of trying to understand each part of that calibration data is to take the firmware, to decompile it, and to find the piece of the firmware which parses that data, and see how each portion of the data is used to, for example, influence the operation of the radio. But also, we can learn more about memory layouts, or about communication protocols which the device might be using with over the USB bus, or another device might have a Bluetooth connection, and with, for example, some custom extension, and really this is the way to do it. So to obtain the firmware, according to the device, you might have more than one possible way of obtaining a firmware. However, usually there is one way which is easier than the others. For example, for another radio, an article on Hackaday was telling that a guy spent 300 euros into an interposer a BGA interposer to put under a BGA flash. This is just to sniff all the transaction over to the flash and then to obtain the content of the flash. But really with the same radio you can either spend 300 euros on one approach, and the other might be just a kernel module distance. So you just have to install a kernel module, and then you can simply, for example, sniff the communication which goes over USB. So mainly the ways in which you can obtain the firmware is either to start from the firmware update tools, because many devices support a field firmware upgrade. How is it called? And you can try to, for example, start from either the Windows application in case it is like that, or an Android app. Every piece of software that performs a firmware upgrade somehow might have in it either the firmware itself or a URL to obtain it from the web. So you can start by reverse engineering the firmware update tools, and this is something which usually, might lead directly to the firmware image, or usually firmware images are encrypted. This is because companies like to they are very jealous about their intellectual property. Therefore, even if it's not a proper encryption, but just a simple obfuscation, for example, take a random chunk of 4K bytes and XOR that chunk repeatedly over the whole firmware. This will make the firmware at least not immediately decompilable. However, it's something which can hardly stop a hacker. This is good for other companies which might lack the capability, the technical capability to understand that. So, according to where the firmware encryption is done, you might have a better luck posing yourself later on in the firmware upgrade chain. So, for example, the update software might handle just encrypted binaries and send them over to the device, and the device might decrypt them itself. In that case, there's nothing to be done. In that case, you just have to dump the flash of the device, just as it is with the MD380. But it might happen that, for example, the firmware is decrypted inside, maybe it's downloaded from the internet in encrypted form, and then it's decrypted before sending it over to the device. In that case, by sniffing the communication protocol, you can obtain a firmware image. And we had success using this procedure with another radio. Finally, so if the only way is to get it from the radio itself, you either can physically read it from the flash. For example, if the flash is an external flash, which uses a SPI interface, you can use a SPI interposer and attach it to the flash chip, and then read it from it directly, the content of the flash. But that might be scrambled, that might be encrypted itself. Another way for some devices like the STM32 based devices is to use DFU. DFU is a protocol. So you see now this is the radio. Okay, so let me go byte by byte. So DFU is a protocol which is used to push firmware upgrades to the device, but it can also be used to retrieve firmware images. So if our device or our radio natively speaks DFU either in its normal operation or in one of the bootloader embedded with the device, for example, a special firmware upgrade mode, then we can simply ask the device using DFU to bring us the firmware image. But things are not always that easy. So let's jump to our device. This is the device I'm talking about. In case you're interested in it, it's very nice for experimenting because a lot of research have been done on this device. Both by our team and by other team like Travis Goodspeed one, and we have a more or less accurate data sheet of the device. So we have the whole electronic schematics, which is good when you have to reverse engineer something, but it's something that you not always have. Let's dig a deep into the hardware. So the device is equipped with a microcontroller manufactured from ST Microelectronics. It's an STM32F4, which means that it contains an ARM Cortex M4 processor. For those of you who do not know what is an STM32, is basically an ARM CPU with a bunch of peripherals attached and a flash in it and some other stuff, which makes it readily available as a whole microcontroller. You cannot just take a simple CPU and just use it as a microcontroller, because you need lots of other peripherals like ADCs, DACs, GPIOs, flash, and many other stuff. So we have 1 megabyte of embedded flash. Then we have also an external SPI flash, which is used for storing the code plugs, which in radio parlance is a term which defines all the settings of the radio, for example, the channels, the contacts, the frequencies, all of that is stored, is just a bunch of binary data which is called code plug. We have a JTAG port, which is luckily exposed into this radio, but it's not properly usable because some of its pins are shared with other pins, and also it's disabled by default using in the firmware of the radio. We have the ROM bootloader, which is something built in every STM32. But we also have the readout device protection, which means that it's a security measure that prevents you from getting the firmware image of the device. And unfortunately, this is enabled by default in the firmware. So we cannot simply ask the radio to deliver us the firmware, because the firmware is read protected during the normal operation of the radio. We have also the HRC 5000, which is this is a digital radio, which means that it is able to modulate a digital protocol over the air, not simple frequency modulation. It does it uses a protocol which is called the DMR, which does 4 FSK modulation, and on top of that time division multiple access and some binary encoded data over that. So all of that is handled inside that special chip, which includes the modulator of the digital modulation and many other stuff, for example, the ADCs. So when we purchase the radio, what we get is also, together with the radio, this cable. So this cable has on one side this weird connection with 2 jacks. I hope you see this. Probably the focus of my webcam is too far, but this is something like a 2-headed jacks with one big jack and the other small one, and it goes to the side of the radio. And on the other side, you have a USB port. So if you tear this apart, I won't because this is glued, because it breaks often. You will find a straight contacts PCB. So basically, this contains just passive components, and the USB pins are mapped into the pins of this connector. So if you take the radio, if you connect it, and if you turn it on, and on your Linux machine, you launch ls-usb-v, then you will see that a new device pops out, and the description string of the device is ST Microelectronics STM device in DFU mode, which is something that you may have seen other times, because it's the default string of the STM32 DFU demo, which is something that you tend to expect from an embedded, the embedded industry, because the less code you have to write, the better it is. So people just take the demo, the example code which has the functionality closest to the thing they are building, and just tweak it to match, which is very good, because in this case, I mean, provided that we recognize that thing, this means that we have a portion of the source code already available. And this is good because, you know, we still might need to reverse engine to decompile the binary, but at least for some functions, we might have already the source code, the matching source code, which is very good. So again, what is DFU? DFU is a protocol which is part of the USB standard, and is the one for firmware, used for firmware updates. So it's a very dumb protocol. It does in its standard form just bidirectional data transfer, but for example, they are blind, so the device does not advertise the size of its internal memory. So the host just try to get data, and at some point the device will return an error, and this means that, you know, there's no more data to be copied over. So it's a very dumb protocol. Remember that it's device centric, so you have the two commands which are upload and download. Upload is on the perspective of the device, so you are uploading from the device to the host, and download is you are downloading from the host to the device. The cool thing for this is that it's a standard which is public. Therefore, there is a tool, a command line tool, which is open source, and it's called Diffuse. This is cool because it allows us to try to read the DFU, the memory of the device through DFU. So, but there's more. Since we are handling an STM32 device, we have to know that ST Microelectronics does not like to implement standard as they are. In fact, they implemented their own extension of the DFU protocol, adding some features which, you know, they were clearly missing from the protocol itself, but still you end up with a protocol which has its weird extension, and not all the tools implement those. So you have to, in this case, the radio does. So you need a tool which properly implements the ST extensions. So the cool part of Diffuse is that it allows basically they implemented the advertisement of the memory segments by the device. So if you have a device which supports Diffuse, you can ask the device to tell you which memories are inside of it, and it will tell you the name of the memory. It will tell you the address at which is mapped in the system, and the size. In this case, for example, the internal flash is segmented, so it will tell you the size of each segment. So it's very neat as a feature. So we know that it supports diffuse, so it's easy. Seems like an easy job. We can start and try to read out using DFU the firmware of the device. Why not? So we will run this command dfu util -d. This selects the USB device with its vendor ID and device ID, so that we are dumping the correct device and on maybe some other stuff connected to our laptop use USB ports. Then we use the alternate mode, and we basically try to read this amount of data using the upload command, which is the one which uploads from the device to the host, and we store the resulting this is for serial. This stores the resulting data into this binary file. So after doing this, however, we will find ourselves a weird surprise. Even though we try to dump this amount, 200,000 in hexadecimal of data, we will find that our image will contain 1024 bytes, which are these, and then afterwards the same 1024 bytes, and then the same again and the same again. So there's something wrong going on here. So we just have the first 124 bytes of some memory region, because we still don't know what we are getting from the radio exactly. So clearly the DFU, about standard compliance. The problem is that the implementation of DFU in that radio, it's not standard compliant, but it's even broken with respect to STM32 DFUs. So probably the fact that the device replies to our upload command is just a leftover, something they didn't remove from the code, but that command is not used by the radio itself, just as it is to dump data. Therefore, its functionality is broken, and we have to find another way to extract the firmware from the radio. So let's try to look at the 1K of data that we got from the radio, and let's try to understand what it is. So what do we know? We know that the CPU inside the radio is the one containing the STM32F4, which is a Cortex M4 CPU, which is little endian. It can also do big endian, but most likely in the vast majority of the cases is configured in little endian mode. And when we do reverse engineering, we have to do some assumptions. Otherwise, we have to do some jumps in the void. Otherwise, we cannot really proceed. And then, experimental trials will determine if we guess it good or not. So, for example, taking the first line of the binary data we extracted from the radio, we see that there are some repeating numbers. For example, this is 008, 008. So if we try to parse these 32 bits and words in a little endian encoding, because the CPU is also 32-bit, and we end up with these hexadecimal numbers, which totally look like addresses. There's some like an offset. They begin at 08 something, and then there's a bottom part which varies. The cool thing of this is that once you get used to that, once you get used to looking at binary image of microcontrollers, you get used to the fact that at the beginning of the image, you see these columns in the binary image, because most of the binary formats begin with an interrupt vector table, which is just a packed sequence, a packed array of 32-bit addresses. And since the highest part is usually fixed, because all the interrupt handlers usually are close by, you see these columns, which are given by the fact that all the 0008s are aligned. So we are recognizing that this might be an interrupt vector table. Therefore, we might be dumping the MCU flash from the 0800 address, which would explain this offset that we are seeing right now, because all the offsets go to pass 0800, and therefore this seems like the beginning of a firmware which begins from 08 and has at these addresses the handlers of the interrupt vector table. So once again, the cool thing of this is that we know the MCU that the radio uses, and the STM32, they have the good thing of being publicly documented. So you can go to the ST Microelectronic website, you can download the reference manual of the STM32, and you will see all the offsets of this interrupt vector table that we are probably seeing here. So if we do some match between the documentation and the addresses we are seeing, we see that the thing actually makes sense, because the first address that we see is the top of the call stack. And since we know that the stack is on the RAM, then we know also that RAM is probably mapped as at 20000000, okay? And then we also know that this is not the RAM, because this contains the code of the firmware, so this probably is the load address into the flash of the firmware. So from this, we know at which address this function actually begins, which might come useful later on, because, for example, if we want to jump into our code, we might override that the function that is at this address and then cause a fault. This will make the device execute our code. But the main takeaway is really the address layout of the device. So to sum up, we know that the code flash begins at 08000000, and DRAM begins, SRAM begins at 2000 and zero with 7 zeros afterwards. But we also know from observation that the firmware updater writes only after 8000C000, and this offset is afterwards, after all the code that we have seen. So we are seeing that there are already two different firmware images. The first one begins from 0800 and then all zeros, and the other one begins at offset C 1000 from that. So we know that probably the 48 kilobytes, which are pretty small binary, probably is the recovery bootloader. And we know that there is a recovery bootloader because the radio has one. We have to put it into this mode for performing firmware upgrades, And we do that by reading the instruction manual, by pressing 2 of the side buttons and turning the radio on. During normal operation, the radio just greets you with some, welcome screen, and this is the normal operation mode. But if we press the 2 buttons and we turn it on, the screen stays black and the LED on the top blinks. So this is a separate firmware from the main one, and since of the 2 functionalities, one seems more complex and probably won't fit into 48 kilobytes of code, then we suppose that that those 48 kilobytes probably contain the code which causes this behavior and allows the radio to be upgraded via USB. Furthermore, by looking at the small portion of code, the 1K of code which we were able to dump, we see that all the pointers are odd. Therefore, this is a characteristic of the FAMB2 operation mode of the ARM CPUs, because in ARM CPUs you can run 2 families of the 2 parts of the instruction set, either legacy ARM code or FAMB2 codes. And this because when the CPU switches from one mode to the other, it does that by checking the last bit of the address during a jump. Therefore, if the last bit is set, the CPU executes thumb2 code. Since we see experimentally that all the pointers are odd, we know that all the firmware is in thumb2, and this will be nice to take into consideration when we will decompile our code. So at this point, we are stuck with that 1K of dump, so we have to find some other way to dump the firmware of the radio. And what we can do is we can start poking around with the protocol that the radio uses outside of the firmware upgrade, which is the one used by the radio for setting, storing the code plug into the radio, so storing frequencies, contacts, all that stuff. That goes through another protocol built on top of DFU. So the manufacturer of those radio really did something very bad protocol-wise, which is they overloaded the DFU standard, which is something meant only for reading and writing chunks of the memory of the device. They use that to send settings to the data, to reboot the data. So they built all sorts of vendor-defined commands on top of the DFU protocol. Therefore, if we want to proceed with that, we have to exploit that DFU dialect used by this radio. To do this, we need to sniff the USB transactions, which are done between the software that runs on the laptop, which pushes the configuration, and the radio itself, which receives the configuration. So once again, to sniff the USB protocol, you have many possible ways. Maybe one of the most comfortable ways is to use a virtualized environment. In this case, it was particularly useful because the configuration software only runs on Windows. And we are the Linux user group of Politecnico di Milano. We don't use Windows as our daily driver. Therefore, all the Microsoft proprietary stuff is better be virtualized. Therefore, by running the configuration software inside a virtual machine and tapping the USB pass-through between the host, the Linux host, and the virtual machine, we can capture the data exchanged over the USB bus. This is natively supported by VirtualBox, which will kindly save the transfer data in a format which is the pcap format, which is the one understood by Wireshark. So you can use the Wireshark tool, which is the same used for network inspection and reverse engineer. You can use that to inspect the communication performed over the USB bus. In case your software, the software you want to reverse engineer, already runs on Linux, and this might be the case, or maybe if you are using Wine to run it, you can use USB pickup. Sorry, this is a software which runs on Windows. So if you maybe disgracefully use Windows as your only system, you can use a USB pickup, which is a software that runs in privileged mode into your machine and is able to sniff the transactions which goes over a USB port. Not a single USB port, but an entire USB hub. So you will have to filter that afterwards, or to use a hub which has only your device connected to it. Otherwise, you will see all the transactions, for example, relative to the movements of your mouse, or to the, to the audio coming out of your USB sound card while you are listening to some music. So that is another way to get some USB traffic. Lastly, you can use a physical USB sniffer. There are many of those. They are usually more expensive. The other two options are like zero expensive, but if you already have one laying around, you can use that and it will be also a viable way. So once we are able to take a look at the transactions of the DFU protocol, then we can try to infer what each command does, and we can do that by correlating the commands traveling on the bus with the commands that we are sending. For example, we will send the code plug upload, which is the one which the function which stores data on the radio. We will trigger that function on the configuration software, and for example, either take note of the timestamp or do a capture which contains only that transaction, so that we can isolate the portion of the protocol which does that operation. And in this radio in particular, what we can see from the commands of DFU is that among the custom commands implemented by the DFU implementation of the firmware, there is one which allows to dump 256 kilobytes of arbitrary data at any position on the radio, except for the one which goes past the 0800C000. That is because, as we said before, the radio has read protection enabled on the flash, but the read protection is not enabled in the bootloader code, the one which goes from 08000 to 0800C000. So the first 48 kilobytes of code that we were inspecting before, we can obtain that. So we went past the first kilobytes of dump, and now we have the complete image of what is the application bootloader. But we cannot go further than that, but this is even more stuff on which to start digging and to start reverse engineering. So to clarify a bit, because things are starting to get complicated, this device, this radio, runs 3 different software layers. It has the ST microelectronics bootloader, which is is written inside the silicon of the STM32. It's immutable. It will always be there, even in case the internal flash fails. And that is executed when, if not disabled with a special command, with a special fuse, that is executed by taking the boot 0 pin of the STM32 and pulling it to 3.3 volts. So to execute that code, we have to take apart our radio and to find which is the pin. Since we have the reference manual of the STM32, we know which pin. We know which pin of the package is mapped to the boot 0 function. So in this radio, this was luckily soldered to a test pad, so it was pretty easy to bridge that with a 3v3, and then turning on the radio does not do anything, which is something worrying, because when you have your radio open, anything when the radios does not blink or does not turns on the screen or does not do anything, then you are always afraid of having already bricked your device, and this is something that can happen. We are doing hardcore hardware reverse engineering, so prepare yourself to turn on the soldering iron, to throw away your money in buying another device, but it will something definitely worth it, because you are doing that for the whole open source community. You are everything that you will uncover, it might be used by some other guys, which might use that information, for example, to start some new development process on the radio. In this case, for example, as I will tell later on, we started from the efforts made by Travis Goodspeed, and if he hadn't soldered on his radio, we probably wouldn't have done what we have done. More on that later on. So that is contained into the ROM, but the CPU flash contains other two software applications, which are the application bootloader, which is the one used for firmware upgrades, that does this nice blinky, and then the main firmware. Okay. So right now, I mean, the first one, there's no use in getting that, because that's is immutable and is just ST microelectronics code. So its functionality is already documented inside the ST reference manual. But the other two, I mean, the third one is the one we want to get to reverse engineer, but right now we are not still able to do that. And the application bootloader is the one we managed to obtain. So we will start by decompiling that one, because now we have the whole code of the application bootloader. And so what we want to do is ultimately defeat the readout protection, which is the one preventing us from reading the firmware. And readout protection can be implemented into 3 ways. It can be in 3 states, let's say. It can be disabled, and in that case, there's nothing to defeat. It's already disabled. But it can also be permanently enabled, and it is done by blowing a fuse inside the STM32. You can do that with the ST tools, but luckily this was not the case of our radio. Our radio had what is called a temporary readout protection. So instead of being always enabled, this feature is enabled manually, is applied in software at each boot. So each time the CPU executes the application bootloader, the application bootloader itself turns on the readout protection before handing over the execution to the main firmware. We can if the application bootloader is doing that, at some point we will find inside that code a memory store function which stores inside the flash optcr, which is this is the symbol into the st libraries, which does controls the rdp mechanism. And we know the address, which is this one, because that can be taken from the datasheet. We know that whoever turns on the RDP will write a 0x55, which is the constant for the enable protection, into the first byte of this memory address. So what we can do is we can take the binary, the application bootloader, we can decompile that and grep for all the memory, for all the occurrences of this constant. And then from that, we will track down if that constant is simply there for no reason, or if that constant is used, for example, to address a store operation, which, for example, might save that byte in particular. And what we will find if we decompile the code of the application bootloader is that at 0044A8 we are storing 55 inside R0. So this is just a tiny portion, but before this, the code in which it is inserted has the right address to activate RDP. Okay, so we can even try another bet and try again to brick our device by taking the bootloader application code and replacing 0x55 with 0xAA, which is another constant that according to the STM32 datasheet means that the RDP protection is disabled. Beware that if we mess up this step and we put the wrong value, for example, the one triggering the permanent protection, then our radio is read protected forever. So, but again, once we have a reasonable confidence of what we are doing, we can try to patch the application bootloader to load it into the radio, and we will see, hopefully, that the RDP protection disappeared. So we did exactly that. We patched 0x55, putting 0xAA. As you can see, this is the binary of the firmware, and this instruction, instead of storing into R055, it will store AA. This R0 value will be then used inside a store instruction that will store into the protection, the RDP control register. So if we patch that, we obtain a jailbroken bootloader, which does not enable RDP. So to flash that bootloader into the radio, we can use the STM32 ROM bootloader. Take care, one of you might think, why didn't we use that bootloader to read the content of the firmware? But again, that bootloader is subject to the read protection mechanism. So we cannot read the firmware, but we can overwrite it. However, when we do so, the STM32 inside the radio will be completely wiped. So the tricky part is that you have to do a dump of the bootloader before you overwrite this, because otherwise you will have lost your bootloader forever and probably bricked your radio. Even if not hardware bricked, you need another radio on which to dump the bootloader to store it back on your radio. But we use the ROM bootloader to store inside the radio the jailbroken application bootloader, and magically doing a single reboot of the device, which will, with the keys pressed, will go into the patched bootloader that will send to the RDP mechanism AA, which will disable the RDP protection. So after this, we can we can use the DFU, the special DFU into the radio to read the firmware, or since we are there, we can use again the STM32 ROM bootloader, which uses just a standard tool, which is proven to work. We can use that to retrieve the firmware, because now we have no more RDP mechanism active. So this is what was necessary to obtain a copy of the firmware running on this radio. And these steps are, although they are specific of this radio, there might be a guide for when doing a similar procedure on another device. For example, especially other which are based on STM32 platform, which is very common, it's embedded into the Xiaomi scooter, the Apple AirPods, the weather balloons, many devices, many radios also run the STM32. So this might be a good guidance. Tomorrow we will see how to take that, the firmware that we obtain through this process, how to combine it with all the information that we've gathered about the memory layout, the fact that some of the code were taken from ST, all of that will be put together to obtain the best decompilation that we can obtain on the original firmware. Okay, so let's see if Silvano is already here.
Yeah.
Okay.
I'm here.
So I will stop my sharing, and you can do your own.
You can keep the sharing if you want. I mean.
Okay.
Just for the first 2 slides, please.
Okay. Sure. I will.
Then I will ask you.
Silvano is a fellow hacker, hardware hacker, and he will talk about
another amateur radio also.
Yes.
India Uniform 2 Kilo Whiskey Oscar, by the way. Okay, I'm here to give you an example of hardware reverse engineering, in some sense, an example of how reverse engineering, or a little of reverse engineering, can be really useful, for example, to repair something. My example is the Motorola GM900. You can, this 90s like block of metal, which is a mobile radio, is in UHF versions, so 400 to 470 megahertz, for example. It's still in use. I mean, on eBay you can find lots of these radios sold as used stuff, scrap stuff, and so on. But why someone wants to buy and use a Motorola GM900? The reason is that these radios can be easily modded, can be easily converted into radio repeaters for analog operation, for digital operation, for whatever. So I got one of these. I bought one of these radios. The seller sold me the radio without any how can I say, confirmation about its correct working. And yeah, I bought one of these just for experimentation. I mean, I'm testing and developing on a new digital protocol, I need a radio on which do some experimentation. I bought one of them, and I got the surprise. I mean, the radio is completely or almost dead, and so I had to do a bit of reverse engineering to determine what the root cause of the malfunctioning is, and yeah, to try repair it. So I share the screen, my screen.
I will minimize mine so that you can share yours. So
you should have my screen. Here it is. This is live video of my radio on my bench. I try to power it up. This is just as arrived from the seller. I mean, unpacked. It arrived. You know, you see it. It's in shape. I mean, it's not torn apart and nothing. But if I power it up, it does just this. It does not react to anything on the buttons. It still keeps blinking. No issue about what the error, the inside error, the inside problem can be. I mean, there is no combination of keys which can give us any clue of what is going on. And okay, you paid 30 euros for this. Okay, you can think either, okay, I lost 30 euros. I can take this thing and throw it up in the trash can. Or another thing you can do is, if you are a little curious at least, is effectively to start analyzing what the cause can be. And first step to do is, for example, finding online documentation. Internet is, in this sense, is your best friend. There is luckily a lot of documentation about Motorola radios, GM900 and so on. These radios have a rear connector, which I can try to show you. Let me power it down just for safety. It has this connector here on the bottom, which is an expansion connector. And you look for the pinout of the expansion connector, which I did here. You have the pinout of the expansion connector. What you get on the expansion connector? You have external speaker, internal speaker, blah, blah, blah. We have bus plus. This means that we have bus plus and bus minus. If you also look around for data sheet on how to program these radios and blah, 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 you get that this bus is a connection to the internal bus of the radio, which interconnects the front panel, the main MCU module, the radio stage, and so on, the memories, blah, blah, blah. And luckily, we have that this bus is broken up on the auxiliary connector. So one natural thing to do is to hook up on this bus and to see effectively what's going on. If we can get any kind of information, any kind of data, any kind of something on this bus, which can help us to see what is going on. To do this, it's better to use an oscilloscope with respect to a logic analyzer, if you have it. Why is it better to have an oscilloscope? Because if you do not have any clue of how the bus works at physical level, the best thing to do is to hook up an oscilloscope, which is effectively a voltmeter. You can see in detail what the voltage levels of the signals of the signal involved in the bus are. We had in another project a very nasty bug involving a signal analyzer and I2C bus. The bug, just to make this short story in the story, is that With the logic analyzer, I implemented a software routine for E2C because I had to do that. Do not go too much in details. I tapped on the communication bus with the logic analyzer. I had the MCU, E2C bus, and the target device to which I had to talk to. I hooked in the middle of this bus with my logic analyzer just to see if my implementation was correct in everything. It was perfectly okay. And what I got? I got that the communication was perfect. The shape of transitions of clock and data were completely perfectly okay. However, I didn't get any sensible reply from the peripheral. Where the problem was? The problem was in the fact that due to capacitive coupling and blah, 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 there was an electrical issue in the bus such that when the MCU released the bus to give the slave device the ability to transmit back the requested data, this bus was floating too much high towards 3.3 volts, and this floating up was interpreted by the slave device as a stop condition. But the point is that in this case, my logic analyzer was not able to detect this floating because it was the reached voltage was too low to be detected as an high logic level. I was able to effectively detect this issue using the scope. So if you have the scope and you need to do bus analyzing, at least at the beginning, the first stages, please, if you can, use the scope, which is a powerful tool which allows you to, avoid a bunch of headaches in this sense. So in this case, in our application, our GM900, what we have? We have scope. Here it is the web interface of the scope. It's a bit minimal, but this is what they offer. Okay, now is everything powered down. You see here, this is the voltage level, this is 0. This is the voltage on this bus. We will sample some data from this bus, and then look at specification and do our diagnosis. Okay, so we have this the scope, the probe of the scope hooked up to the bus. Radio is off. I configured the scope for 2 volts per division here in the y-axis. I configured it for let me refresh. It does not auto refresh. 20 milliseconds of capture time. I configured the trigger, the trigger for a new capture as edge. So when there is a change, source is channel 1. Slope is falling because I determined that this bus is active high. So when there is no traffic, is fixed to 5 volts. So there is a change from 5 to 0 when someone tries to transmit data and other stuff. Trigger to normal mode, which means trigger and start a capture whenever you see any change. Now, if I did not short-circuited anything while I flipped my radio, we can try to do experiment. So we can start. Okay, it captured. I need to refresh the screen, sorry for that. And here it is. This is some data which has been transmitted by the radio on the bus, on the internal bus, to which we are hooked with the scope at the power up. With normal trigger, basically we start a measurement and in the exact moment where there is a change from 5 to 0 volt. Now I zoom and then I zoom also on computer. Okay, screen refresh. Here it is. Let me see if what happens. Okay. Okay, I hope this is a bit better. I mean, it's one of the defects of this scope is this one. Okay, I left protocol decoding engaged. Anyway, what we have this, we have 5 to 0 transition, then we have something. So at the boot of the radio, there is effectively something which is passing on this bus plus. And okay, what is this bus plus? Again, internet is your best friend. Okay, internet is your best friend. You do a bit of search around, and then finally you, maybe, I hope this does not happen all the times, you get effectively the specification of the protocol which goes on this radio, which is called SB900 and 9600 serial bus protocol menu and blah blah blah. And here you start thinking, okay, is 9600 is serial? Should be plain old RS232? Yes, indeed it is. Okay, in 5 to 0 volts, but effectively it is a plain old serial protocol. Then you read a bit, you go through physical bus, and it does say that serial data transmitted at 9600 bits per second on a bidirectional bus. By access to various processors in the system is obtained via the bidirectional data line and blah blah blah. So going here now, we have bus plus here in busy, which is another line which gains a new meaning once we read the specification, and access to is obtained blah blah blah, and the bidirectional handshake line. Okay, going through the specification, we get blah blah blah. Audio routing is bus protocol. Device accesses the bus by first checking to see that the bus line is inactive, and then if it's not free, you have to wait, otherwise you can talk and blah blah blah. This means that we have access to the bus on the accessory connector. We can try to see what's going on, and also in our application, why not, we can use this bus to manage our radio. For example, you do a companion PCB with a microcontroller which is doing fancy stuff. If you need it, you can also add support for this bus and remote control your radio, for example. Okay, so we have this bus, and we see that on this bus are exchanging some messages, which typically specification says have an address packet, which is indeed a byte, 2 data bytes, an opcode and cyclic redundancy check packet. Okay. Okay. So then it's a lot of blah blah blah. What we can do again with our scope, we have the signal. We can use the decode utility, because nowadays, like 99% of the scopes have some software utilities on board, which allows you to decode protocols. For example, if I go here, okay, let me put in full screen. You see, this is the code menu. It's protocol, UART, signal, blah, blah, blah. But for example, this scope, just to make an example, I'm not selling scopes in my life. This scope allows you to decode I2C, SPI, UART, which is basic serial, CAN bus, and LIN, which is another protocol used in automotive. But anyway, in my case, I used just because I had it, but if you don't have it, and with the scope, if you look that it's logic signal going from 5 to 0 and so on, okay, at this point you can use logic analyzer if you want. I mean, first step with the scope is just to give you a complete picture of what's going on. But anyway, I'm lucky I have a scope which does protocol decoding. Specs says that is a serial protocol. Okay, let's try hookup protocol decoder, UART mode, and effectively it's transmitting 5 bytes as dictated. So here we have 0, 0, hex value 0. Then we have hex 82, hex 1, then 3B and 2D. Looking at the specs, we have that these bytes are, first is an address byte, then we have 00 is address, then 82 and 01 is data, and then we have opcode, and then we have CRC. Okay, then again, this is a lucky case. I mean, it's not so common that you have specification. So just as a lucky and easy case. Going along, we have the addresses. Should be, here it is. We have the addresses. 00 is entire system. So this is a broadcast packet for the entire system. We have content and we have 3B. I can close this. 3B, if you go, I bookmarked it. Please go. Okay. Is power up status. Is normally broadcast by each device on power up, indicating the result of local self-check routines. So is first byte is 000 something, then is data 1, and blah blah blah. Okay, we get 83 in okay, sorry, I have to a bit to remember. So data 1 contains effectively our diagnostic. Each bit of data 1 is set to 1 when an error condition occurs as described above. Okay. What we have here? We have 82 and 01. The first byte contains status. The second one is the device address. In our case, is 0, 1 because we have only one radio on its own, so it takes 0, 1. It's the first of something. In this case, it's nothing. Okay, let's decode 82. It's bit number 7 is set. Fatal error. Okay, let's start. The second one is bit number 1 because is 80 is the upmost, then 2 is the second bit from the right, which means EEPROM failed checksum. Okay. EEPROM failed checksum, if you dig a bit more in how these radios are built and are made inside, you will get that you have the flash memory, which you cannot write, which contains the program for the main MCU, and you have a writable in some sense EEPROM, electrically erasable programmable read-only memory, which contains the so-called code plug, which is all the configuration for channel, frequency, and so on. If we have the fatal error, which is fail of the checksum, it should be that we have corrupted code plug. So the next step, which I cannot show you here because you need an old computer and run an old DOS program and hook everything up, and so a big messy. Okay, so you have a failure in your code plug. In this case, you finally get at least some clue of what's going on your radio. Next step is to try re-flashing the code plug. And also in this case, I discovered that having a scope at hand or a logic analyzer at hand is very, very useful because you can effectively see the interaction between the radio and the computer. Because remember, this is a plain, an old radio from 90s. And software is very, very old. It runs only on DOS machines. There is almost anymore, there is no availability of programming cables for these devices, at least. So you have to understand how the protocol works. You have to build some kind of programming interface for your radio. You have to hook it up to the radio. You have to hook on the other side to the computer. It's better to put either a logic analyzer or a scope for debugging purposes. I did this, and I obtained that computer is talking to the radio is understanding nothing. So there is something broken in between, which I still have to reverse engineer, and in which I still have to do some experimentation. This is I mean, it's not a huge, big and fancy example, but it's just to give you an idea of how sometimes you need effectively to reverse engineer something to make it work again. I did something like this in many other situations, like power supplies. I had to fix an alarm system by reverse engineering because there was no schematic. There was some nasty issues on the electronic board and so on. So effectively, reverse engineering is a thing if you need to repair something. And also, this is fun fact, in this case, I was very lucky to obtain the specification of the protocol. I mean, it's a very common case. You do not even have the specification of the protocol, so you have also to reverse engineer the protocol, see what's going on, try to debug, poke around, and so on. So this is lucky case in some sense.
Okay. Okay, so Silvano, shall I go ahead?
Sure.
Okay, so talking of things, a question which we get asked very often, but we even asked that ourselves. So we talked about ham radio because I showed you a radio as an example of device to be reverse engineered, and also me and Silvano, we are both ham radio operators. So is ham radio still a thing? And now the spoiler will be yes, it is. And it is for a very precise set of reasons. The fact is that most of you probably are either computer science engineers or electronic engineers or some other technology related engineers. Therefore, you probably are already interested to technical stuff. The interesting thing about radio, and it's something that hasn't changed since the early days of radio in the beginning of last century, is the fact that ham radio gives you a very nice playground on which to play, which in the modern days ranges from the, let's say, more electronic side, from the analog part of the electronic side, from the digital part of the electronic side. Then you have the microcontroller, because most recent radios have an MCU like an STM32 that we have here. And so you have a firmware, but you also have, for example, you might have a graphical application running on top of that. So right now we are already ranging from the most lower level electrical signal stuff to the most higher level graphical user experience stuff. So, and we are just on the basically on everything which is not properly about the radio, about the RF part. Even that is very interesting, because even though for example, neither me nor Silvano, we are not RF engineers. However, in a ham radio, you don't need to be that to have fun, to enjoy, to use that, because the simple concepts are very easy to grasp, to understand. Analog FM modulation, you can first understand it, and it's even explained in some courses of the Politecnico di Milano. But then the big step becomes, for example, in visualizing it. Thanks to the software-defined radios, which are devices which were originally meant to be television USB sticks, but someone reverse engineered them and discovered that they are basically a general purpose receivers. With a device like that, like an SDR, you can, for example, graphically visualize how a frequency modulated signal looks like. You can take the remote control of your garage door and use it and see graphically how its protocol looks like. And with ham radio, you can use that to talk to other people. And you can, for example, either try to go as far as possible or try to make some fancy radio contacts. Like, you can we have in the Europe from Brazil to China and including all the side of the earth that we are on. In Europe, we have visibility over a ham radio geosynchronous satellite, which is something very interesting because you can, if you are a ham radio operator and you are equipped with a scrap dish and other pieces of electronic, you can receive or even transmit to that satellite. And for example, make a relayed contact with someone which is in Brazil and has the same similar equipment as your own. Or other people, for example, they launch weather balloons and they try to have other people around the globe receive those packets. So you have many. Ham radio is a dense hobby in which you really probably you won't be good or innovative in every piece of the spectrum. That's very hard, but really it's a hobby in which you can find an entertaining practical application of, for example, what you are studying or of what you are passionate about. And for example, for my case, I am myself a computer science engineer. Therefore, I'm used to just dealing with software. And for me, ham radio is even, for example, climbing on the roof of my home and pulling up a pole and putting an antenna on top of that, which is something that eventually I can then use with some software to make nice things. But really, it's a practical way of putting down your technical knowledge. And Silvano, if you have some other thoughts about why is it worth it to be a ham radio operator? Oh yeah, one thing, you get this almost for free if you are an engineer, because if you certify to the Italian Ministry of Communications that you have done certain, this is true in Lombardy, that you have taken certain signal and radio related courses, which most of them are in the standard studies of the Politecnico engineering degrees, you don't have to do an examination to get your license. You just have to wait a few months and do some paperwork, and you are ready to legally transmit in a vast number in different frequencies, from the one used by this radio to the ones, for example, which are the lower one, the HF one, which were the same used, for example, before the invention, before the deployment of submarine cables to perform communication across the Atlantic. And now I've talked enough, so Silvano, if you want to share your experience.
Yeah. Okay. Sorry, I was just having a look on the chat. There is one question. Don't you still have to do the non-technical parts of the test? The answer is no. I can tell you in detail that not now. Anyway, back to the topic. Why is fun ham radio? Because it's pure experimentation. I mean, if you are a ham radio operator, you have freedom to build your radio receivers, your radio transmitters, to transmit, to invent new protocols, to test existing protocols, to bring open source to existing protocols. You can do almost whatever you want in, okay, not breaking laws, that's obvious, but I think that the key point is really is the freedom of experimentation, for example. But by the way, just because we are talking about reverse engineering, there is a lot of effort in reverse engineering of radio protocols. Notable example is the SpaceX telemetry stream, which has been reverse engineered by ham radio operators, which have the equipment, which have SDRs, antennas, and so on. And just because they tried to receive these telemetry streams. Sorry for the telephone in the background. I was saying, yeah, there is also an interesting part of reverse engineering of existing radio protocols, for example. SpaceX is one case. So you have really freedom of experimentation. And another example, I have a bunch of them here, is meteorological zones. These stuff here. This stuff here is basically a radio transmitter with a temperature and humidity sensor on board. They are used for measuring the atmosphere. They are attached to balloons at midnight and midday every day by meteorological service of Italy, Spain, and whatever. And then they fall back. When they fall back, they hit ground, and if you find any of these stuff, it becomes yours. What's inside? A powerful GPS, a powerful radio transmitter, an STM32 microcontroller, and sensors. Okay, you have one of them, and what now? You can do, if you want, and in this case, if you have a license, because to transmit on those frequencies, you need a license. What you can do your personal weather station. You can do your personal tracker for things. You can do your own balloon. You can, and nobody did at a deep level. So nobody up to now have a deep understanding of how those stuff work. You can reverse engineering that stuff and use its internal sensors and make your own weather balloon if you want. So ham radio is just, in some sense, can be considered an excuse for really a lot of stuff and experimentation, reverse engineering, implementation, new things, whatever, I think.
Very good. And if you need some more information about how to become, at least in Italy, a ham radio operator, please keep in touch, for example, through the POuL Telegram group, and we can support you. We have done that for many of our friends and ham radio peers, so we know we can give you guidance on how to do that as quickly as possible and without much stress. And now let's talk about the last topic of this episode of the ReverseIt course, which somehow popped up in between until now. So this is OpenRTX. And what is OpenRTX? It's our great example of reverse engineering. Is a project that me, Silvano, and Federico and Frederick are building, and it's meant to be an open source modular firmware for all kinds of radios. And why is something like that needed? First, because even to use the radio as a radio itself for its original functions, you can build, writing your own code, something which works better than the original one, especially for low cost radios from the Chinese market like this. The original firmware which you get has a terrible user experience, either because of the bugs or because it's simply badly written. And by writing your own code, you can, for example, try to consider everything that you like about that you would like to have in a radio and simply program it, and you will have it in your radio. So this on the purely radio function is cool by itself, but also you have the fact that you are really having the control of the hardware you own by being able to compile and run your own code, just as you would do by running Linux, for example, on your laptop. Then there is another reason which is becoming predominant in our project, which is the fact that among the ham radio protocols, you have the analog protocols, which are the one which does plain frequency modulation or other variations, but they transmit an analog signal, and those we have those since the beginning of last century. So everyone can build a device which transmits and receives those protocols. However, when digital protocols came out, this is no longer true, because unfortunately, when digital protocols, which are the one which instead of sending through some analog encoding directly the voice, they send with a digital encoding some data frames which contain a digital representation of the voice. All of this protocol, all the one that we have commercially available today, were developed by industry players, which for various reasons, for example, the fact that in the 90s, when they developed them, the only voice encoder, the only vocoder, so the only piece of hardware or software which takes the analog voice and produces a digital audio stream, the only one available at the time was proprietary and patented. This has led to the fact that right now all the digital protocols that we have rely mandatorily on a proprietary vocoder. This is especially bad because while for analog protocols you can build your device and start receiving or start transmitting if you are a ham radio operator, for digital modes, doing that, for example, writing a software on your laptop which takes the decoded signal from an SDR and turns it into the voice. So a decoder, for example, of this protocol, the DMR, would be illegal, would be plain illegal, because you would have to take a commercial arrangement with the owner of the patent of the AMBE, which is the name of the codec, and spoiler alert, you will never get a reply from those because they don't care about community projects. Therefore, either you risk money, you risk, facing a trial to experiment, which is something that many of us would be willing to do, or the alternative is, just as we created with Linux and with many other open source projects, an alternative to proprietary system, there is a a group of people which is doing exactly that for digital protocols. This project is called M17, like Mike 17, and you can find them on the web. We will provide suitable links in the slides, and they are building a digital amateur radio protocol from scratch using only open source technologies and code and open protocols. Therefore, with a protocol like that right now is being designed, is still it's in experimental stage, but with a protocol like that, you really would have back the freedom to experiment, to create your own machine, to use something which is as free as all the older analog techniques. And I was talking about OpenRTX. What's between M17 and OpenRTX? Right now, M17 can only be used on either devices which rely on an external device like a smartphone or an SDR. With OpenRTX, we are trying to bring M17 to commonly available commercial radios like this. Therefore, people don't have to spend lots of money. People can buy a cheap radio, can compile their own open source software and run the open source free digital protocols on them. So this is one of the other advantages of a project like this. But you know, again, once you are able to run your own code, the sky is the limit. For example, a member of the community, another ham operator, built a tracker for low Earth orbit satellites directly into the radio, so that you can have the predictions for when the next satellite will pass. You can have the radio automatically correct the Doppler effect by shifting frequency, and all of this stays on the radio without external connections. This is an example, but many more can be done, and we are trying to we do not only run on this radio, we run on 5 families of radios, and we are trying to build stuff so that people can actually contribute, can actually build the project on their machine, can actually write their own code, and we really believe in a community-driven effort. And to reach us, you can follow us on Twitter, you can go to our website, or even join our Discord. And Silvan, did I left something out?
No, I mean, I will say no. No, one thing that comes to mind is also, and this is very important, with open source, you can bring something which original firmware does not have, and also something which original equipment manufacturers are not interested in, which is, as some people asked us, which is voice prompts and tools for visually impaired ham radio operators. This is something which original firmware does not have, and I would say no one among the manufacturers has the interest in implement such a thing. And that's the key of open source. Also, I would say, is also accessibility. I mean, it's an example. It's something which you can do. And yeah, that's it. I mean, it is another piece of a big puzzle you can have. That's it. Then another piece is that effectively our project is heavily based on reverse engineering. Really heavily based on reverse engineering. I do not know how many pieces, various aspects we covered by reverse engineering stuff. So,
which is also a fun activity sometimes.
Yes. I'm not saying it's not fun. It's fun and useful.
Exactly. And together with the development effort, we are also trying to build a knowledge base of all the devices that we are working on, so that even people might not be interested in our project itself, but maybe want to start something new on the hardware, they should have the knowledge to do that. Because really, if you don't have any knowledge, your effort will be only in reverse engineering. Once you know the details of the platform, you can build on top of that and you can create things. Ourselves, we started from the works of Travis Goodspeed and its work in modification of the original firmware, from which also parts of this presentation were taken, which paved the way, which gave us some insights about how this radio works. Therefore, we were able to really stand on the shoulders of the people which did some reverse engineering before us, and bring on the frontier of the knowledge about these commercial platforms. And I believe that this is today for now. So this talk has been recorded, and you will have the recording of the talk and also the slides available in the next days. Again, for those of you who maybe have joined later, this episode, also the whole ReverseIt course, is organized by Politecnico Open Unix Labs, which is the Linux user group of Politecnico di Milano. And if you have any questions, maybe we have a few more minutes to answer to maybe some questions on the chat. So is there still some question on the chat which was unanswered? For the ham radio test, I believe that, I mean, for my experience, an engineering degree covers is enough for having your license. This is not true for all the regions of Italy. For example, in Sicily, you have to do the test nonetheless, but at least in Lombardy, really, you just have to do paperwork to get it. And
it seems that they have changed the regulations.
Okay, so yeah, so
they mixed up the cards anyway.
Yeah, they changed it very recently, but yeah, we will for sure follow you into the process. And what about? Yeah, you're welcome, Valerio. Okay, so I believe this is for now. If you have maybe some other questions, we have still. We will be here tomorrow at the same hour. So 15 UTC, which is 17 of Italian time. So thank you for being here, and see you tomorrow eventually. Have a good evening.
Goodbye.